So now let's try to generalize this result. See if we can get an even better bound on what the on what the sum of the series is. So I want you to recall something from the first section on the sum of infinite series, and that had to do with the partial sum. So recall that we use the term Sn to refer to the partial sum of a series, of an infinite series. In other words, the sum of all the terms up to some index n. So in the case of our alternating series, that means that Sn is just going to be a1 minus a2 plus a3 minus a4. But instead of going on forever with this dot dot dot, we're going to stop at n. This is actually just the sum of a finite number of terms. So what we want to do is we want to prove that the difference between s and its nth partial sum is less than the next term of the series. We're going to do that in the special case where n is even. And after I've done this, I'm going to put up the odd case, which is just the mirror image of that. And then we'll put them together and see what result we come up with. So, by the way, I know that the word prove in something this abstract gets a little scary. So even though I normally change show to prove, here let's just say show. Maybe that'll be a little less scary. Okay, so what we want to do is consider what s minus Sn is. So s minus Sn is, if you write it out, this is going to be a1 minus a2 plus a3 minus a4 plus a5 minus a6, going on forever, and we're going to subtract from that just a1 minus a2 plus a3 minus dot dot dot. We'll go up to an. So in other words, what we're doing really is we're simply taking the first n terms out of the series, and what that leaves us with is that s minus Sn is going to equal an plus 1 minus an plus 2 plus an plus 3 minus an plus 4 minus an plus 5 minus an plus 6. Sorry, I'm putting in, there we go, minus plus minus plus minus. Okay, that's good. Plus dot dot dot. So it's the series S, but with the first n terms removed from it. Now let me just pause to explain why I insisted that n be even. Because what we can see is that the even numbers are the ones that are always being subtracted. So what I wanted was, for this term here, I wanted this to land on a positive term just because it would make the algebra easier. And like I said, we'll do the mirror image where we land on a negative term. I'll put that up after we're done, but let's just do it assuming that this is a positive term. So now we can do basically the same thing that we did in the previous example. What we can do is we can simply observe that if I group the terms this way, then what we have here is a bunch of positive terms like that. And we can easily see that therefore this is greater than 0. Okay, and then you can probably imagine what I'm going to do next. In order to prove that it's less than an plus 1, I'm just going to regroup the terms slightly differently by writing an plus 1 minus an plus 2 minus an plus 3 minus an plus 4 minus an plus 5. I won't go on because you can see what we're doing here. So as you can see, even though, let's say, in the original writing of this, an plus 3 had a plus sign in front of it. Once again, I have to use the distributive property, so that's going to be minus negative an plus 3 in order to equal the same thing that I wrote up here. And still, what we get is a bunch of positive terms. So this is positive and positive. And what we can see is that therefore this number is going to be less than an plus 1. So putting this all together, we see that s minus Sn is greater than 0 and less than an plus 1. So we can say that s minus Sn is less than an plus 1, but greater than 0. And we've now proved that claim, that this combination of statements is true. Now, what does this mean? The thing you have to realize is that, the thing you have to realize is that S is the sum of the whole series. In other words, all infinity terms of it. And Sn is the sum of the first n terms, or at least the terms up to index n, depending on where we start. So the difference, S minus Sn, is the difference between the exact sum and its approximation by the first n terms. So when we look at the expression s minus Sn, what we're really asking is how bad of an approximation is using the first n terms to approximate the whole series. And the answer is it's going to be no worse than the next term in the series. I'll show you an example a little bit later of that demonstrates this principle. Let me just put up here in case you want to look at it. This is the case where n is odd, whereas you can see we land on a negative term for n plus 1, and it just becomes the mirror image of this. You can pause the recording if you want and study this if you're interested, but basically it works the same, just with a minus sign in front of it. So what we end up with is the fact that we end up sort of with the fact that if n is even, then s minus Sn is greater than a n plus 1. Or if n is odd, then s minus Sn is less than negative a n plus 1. So in other words, what we have here is that s minus Sn is somewhere between negative a n plus 1 and positive a n plus 1. If you're astute about how absolute value works, that means that the absolute value of s minus Sn is just less than a n plus 1, since a n plus 1 is always positive. This is the error-bound formula for alternating series. So this is a formula that we're actually going to make a little bit use of, and we'll see that shortly. So I just want to make one more point about the error bound, which is really a different form of the error bound, and that's that the sum of an alternating series, again, where the alternating series is defined in the special way we have, that it's based on a positive decreasing sequence. When I have that condition, the sum of the alternating series lies between any two successive partial sums. And let me just show you why. It's really a very similar sort of an argument. If I write out the sum like this, s is equal to a1 minus a2 plus a3 minus a4, etc. Let me just do this in the specific case of s6 and s7. So if I were to write out, let me take this part here and just replace this with s6. Then what you'll see is that I can write that s is equal to s6 plus the rest of the terms. But look how I'm going to group them. I'm going to write a7 minus a8 plus a9 minus a10 plus etc., where of course these are all positive. So what we can see is that s is equal to s6 plus a bunch of positive terms, and therefore s must be greater than s6. Now we can do the sort of mirror image of that if we use S7. So what I'm going to do is, let's call this S7, in other words, the sum of the first 7 terms. And now what I've done is the same thing that I've done in the past. I'm taking the remaining terms and grouping them in this way, but I have to distribute the minus sign. So you see here, all the odd terms are positive in the original series. A9 is positive. You don't see A11 there, but it's going to be positive. So when I distribute the minus sign, I have to turn this into minus quantity A8 minus A9 minus quantity A10 minus A11, etc., where of course these are positive. So I have S is equal to S7 minus a bunch of if S is equal to S7 minus A8 minus A9 minus A10 minus A11, it's clearly equal to a bunch of positive, so S7 minus a bunch of positive numbers, so that means that the sum is going to have to be less than S7. We put together this statement and this one, and we get that S is going to be greater than S6, write that backwards, so that the S6 is the smaller one, and that S is also going to be less than S7, and we see that the total sum S is going to be between S6 and S7, and since obviously this argument could be made for, I could have chosen any pair of successive partial sums. I could have chosen, say, S100 and S101, and I'd get exactly the same argument. We can see that this is still going to be true, that it lies between any two successive partial sums.